Here are the top 10 most important things you need to know about matrices. Must know number 1. What is a matrix? A matrix is a rectangular array of numbers arranged into rows and columns. So here's a sample of what a matrix would look like. And the size or order of a matrix is said to be m by n, where m is just the number of rows the matrix has, and n is the number of columns. If I wanted the size of this sample matrix, I notice that it has 2 rows, and I'll number those rows, row 1 and row 2, and it also has 3 columns. And I'll number those columns 1 through 3. Because this matrix has 2 rows and 3 columns, we could say that this is a 2 by 3 matrix. And let's give this matrix a name. Let's say this is matrix A. So I could say matrix A is a 2 by 3 matrix. Now for this matrix A, there are 6 elements, and all 6 elements have a unique position within the matrix. The position of all of the elements that make up matrix A could be defined based on their row and column indices, I and J, where the index I states what row number the element is in, and the index J states what column number it's in. So all 6 of these elements have a unique position that can be defined using this notation. So how that would look within the matrix would be this element here that is in row 1 and column 1 would be element A1, 1. And this element, which is in row 1, column 2, would be element A1, 2. And this element, which is in row 1, column 3, would be element A1, 3. And I'll also fill in the notations for the elements that are in row number 2. Now that you know what a matrix looks like, how to describe its size, and how to reference any of the elements in a matrix based on its row and column, let's do an example. Let's say I have matrix B. Let's state the size of this matrix, and also find the value of element B24 and B32. To define the size of the matrix, I need to know how many rows and columns does it have. Remember, rows are horizontal, so we have 3 rows, and columns are vertical, so there are 4 columns, which means this is a 3 by 4 matrix. Now, if I want element B24, remember the first index is the row number, and the second index is the column number. So I'm looking for the element that is in row 2, column 4. I can see based on where those lines intersect that I'm looking at that element right there, which has a value of 4. And for element B32, I'm looking for the element that is in row 3 and column 2, which would be this element right here, which has a value of 5. Must know number 2, basic matrix operations. The basic operations I'll show you in this section are adding and subtracting matrices and scalar multiplication. Let's start with adding and subtracting matrices. The first thing we should note is that to add or subtract matrices, the matrices must be the same size. And all you have to do to add or subtract matrices is add or subtract their corresponding elements. So for example, if I have matrix A and B that are both 2 by 2 matrices, the sum of those 2 matrices would also be a 2 by 2 matrix made up of 4 elements. To get the element that goes in row 1, column 1, I would just add the elements from matrix A and matrix B that are in row 1, column 1. So I would do A11 plus B11. And to get the element that goes in row 1, column 2, I would add these 2 corresponding elements, and the same pattern for the elements that are in row 2. So let's do a quick example of this. Given matrix C and matrix D, let's find the sum of those matrices. Because the original 2 matrices are the same size, they're both 2 by 3, I know when adding them together, I will get a 2 by 3 matrix as well. To get the element that goes in row 1, column 1, I'll add the corresponding elements from matrix C and matrix D. That would be 1 plus 7. And then for row 1, column 2, I'll add 2 plus 8. And then for the element that goes in row 1, column 3, add the corresponding elements 3 and 9. And then I'll follow that same rule to get the elements that go in the second row of this matrix. And now let me make some room so that I can simplify all of those elements. The elements in matrix C plus matrix D simplify to 8, 10, 12, 14, 16, and 18. Let's now move on to scalar multiplication. For scalar multiplication, each element of the matrix gets multiplied by the same factor. And when doing this, the matrix stays the same size. So if we have some matrix, matrix A, I could multiply that matrix A by some scalar, I'll call that scalar K, to get the elements that go inside of that matrix. I would just multiply all of the elements of matrix A by the scalar K. Let's practice that with an example. Given some matrix, matrix B, let's find what 3 times matrix B would equal. And I could calculate each of the elements just by taking all 6 of these elements and multiplying them by the scalar 3. And then I could simplify each of those elements by doing the multiplications. So 3 times matrix B would have the elements 6, 12, 18, 3, 9, 15. Must know number 3, elementary row operations. There are 3 operations I'm going to show you in this section: interchange, scaling, and replacement. But before I show you those operations, it's time we talked about one of the main applications of matrices, and that's representing systems of linear equations. So if we have a system of 3 linear equations, there are a couple different ways I could represent the systems using matrices. The first way, which we'll talk about a lot more later, is the matrix form. Matrix form is the format AX equals B, where A is what's called a coefficient matrix. And to create that matrix A, I just have to look at the coefficients of the variables in these equations. So for row 1 of matrix A, I just look at equation 1, and specifically, what are the coefficients of the variables? They're 4, negative 1, and 2. And then to get row 2 and 3 of matrix A, I just look at the coefficients of the variables from equation 2 and 3. X stands for the column vector of the variables that are in the equations. The variables in the equations are X, Y, and Z. And B is the column vector of the constant values that the 3 equations are equal to. And what we're going to be doing in this section is actually combining together the coefficient matrix with this column vector of constant values to create what's called an augmented matrix. When combining them together, we just place these constant values as a 4th column combined with this coefficient matrix. And often you'll see a vertical line separating the coefficient matrix from the constant values. And now the whole reason we would want to rewrite this system of equations in this augmented matrix is so that we can perform these 3 operations to make the solution or solutions to this system easier to find. Because no matter which of these 3 operations we do to an augmented matrix, the result is a matrix that has the exact same solution set. So let's look at these 3 operations, and then in the next section, I'll show you how they can be used to find the solution to a system of equations. The first operation is interchange, which just means you're allowed to swap 2 rows with each other. So if we start with this augmented matrix, I could, for example, swap row 1 and row 2 with each other. And the notation for that is you would write row 1 and row 2 are switching places with each other. And when we do that, we get a new matrix where row 2 of the original matrix is now up in row 1, and row 1 of the matrix is now down in row 2, and row 3 stays exactly where it is. The second operation is scaling. That just means you're allowed to multiply any row by a scalar. So let's continue on with this matrix here. I could, for example, take row 2 and multiply it by 3. So I would multiply row 2 by 3, and then whatever those answers are, put all of those values into row 2. Doing that will create a new matrix where rows 1 and 3 stay the same, but the values in row 2 need to be tripled. And the last operation is replacement, which means you can replace any row with the sum of itself and any other row in the matrix. Continuing on with this matrix, what I can do is I can replace row 3 with the sum of row 3 plus row 2. I'll communicate that by saying row 2 plus row 3. That result I'm going to put into row 3. Now an important part here, because I'm adding row 2 and row 3, the result of that can only be put into either row 2 or row 3. It can't go into row 1 if that's not included in the addition. And also, I could have put a multiple in front of either of these rows as well. So I could have done, let's say, 2 times row 2 plus row 3. But I'll keep it simple for this example. Creating this new matrix, I notice only row 3 is being replaced. So rows 1 and row 2 are going to stay exactly the same. But row 3 is going to be replaced with the sum of row 2 and row 3. So when I add the corresponding elements of row 2 and row 3 together, when I add the first elements together, 12 plus 2 is 14. So that becomes the new element in row 3. It becomes 14. Negative 3 plus 3 is 0. 6 plus negative 4 is 2. And 21 plus 9 is 30. Looking back, even though we started with this matrix here, we performed 1, 2, 3 different elementary row operations on that matrix and ended up here. This new matrix we've created has the exact same solution set as the original matrix. And in the next section, I'm going to show you how we can choose which of these operations to do so that we end up with a matrix that shows us the solution to the system of equations that we're working with. Must know number 4, reduced row echelon form. Let's say we had a system of 3 linear equations. I could use an augmented matrix to represent this system. To write the augmented matrix, the first thing I do is create the coefficient matrix, which I do by looking at the coefficients of all the variables in all the equations. So for equation number 1, the coefficients of the variables are 2, 1, and 6. So that becomes the first row of my coefficient matrix. Row 2 would be 3, 4, 3. And then row 3 would be 1, negative 2, negative 4. And I augment that with the column of constant values that the equations are equal to, 7, negative 8, and 9. What I want to teach you how to do in this section is how to use elementary row operations to convert this augmented matrix into a matrix that's in reduced row echelon form. And the reason why we would want the matrix in this format is because it's easy to tell from that format if the matrix has no solutions, if it has infinite solutions, or if it has one solution, what that solution actually is. And any matrix that is in this format has a structure that follows 5 rules. Number 1, if there are any rows of the matrix that are all 0, they're at the very bottom of the matrix. Each leading entry is in a column to the right of the leading entry above it. So if we look at row 2, its first non-zero number, its leading entry, is right here. It's this 1. Notice that leading entry is in a column that's to the right of the leading entry that's above it. And number 3, all entries in a column below a leading entry are 0. So if we look at the leading entry from row 1, everything below it is a 0. Now any matrix that follows those first 3 rules is in what we call row echelon form. But for a matrix to be in reduced row echelon form, all the leading entries also have to be a 1. Notice they're all 1s. And each leading 1 is the only non-zero in its column. So looking at the leading entry from row 2, not only is there a 0 below it, but there's also a 0 above it. It's the only non-zero number in its entire column. And to get a matrix into this reduced row echelon form, there is a process called Gaussian elimination that we're going to follow. So let me start by copying this augmented matrix down here, and we'll start doing some elementary row operations. Now the first thing we want to do is begin at the leftmost non-zero column, so right here, and make a non-zero entry, the pivot at the top. Well, all of the entries in this column are non-zero, so we could use any of them as the pivot at the top, but I notice in reduced row echelon form, eventually I'm going to want a 1 there, so we might as well make this one the pivot at the top of that column. So to get that 1 to the top of the column, we'll have to swap this entire row with the row that's at the top. So in order to get this 1 up to the top of the column, we can swap all of row 3 with all of row 1. So this 1 is now called our pivot. And what we want to do next is make all of the numbers below that pivot, so the 3 and the 2, we want them to be a 0. I'll have to do that using the replacement operation. I'll start by making this 3 become a 0. I could do that by replacing all of row 2 with row 2 minus 3 times row 1. So row 1's actually staying exactly the same. I'll leave it as it is. But I'm replacing all of row 2 with each of these entries minus 3 times those entries. And now I also want this 2 to become a 0. So I can replace all of row 3 with row 3 minus 2 times row 1. Now that we've created zeros below our first pivot, we're going to ignore the first row and repeat that same process for the remaining submatrix. We're going to look at the first non-zero column. We're going to make a non-zero value be the pivot. I might as well let 10 be the pivot, and then make everything below that 10 become a 0. So I just need to make this 5 become a 0. We'll continue doing that down below. Continuing with this matrix, I can make this 5 be a 0 by replacing all of row 3 with 2 times row 3 minus row 2. We could now get our answers by writing the 3 equations that these rows correspond to and using back substitution to get the answers for the variables. But we're going to continue on to get this matrix into reduced row echelon form to make it more obvious what the answers are. So what I have to do now, going from right to left, is create zeros above each leading entry, and also make the leading entries all be 1. Looking at row 3, it would be easy to make this leading entry be a 1 just by multiplying all of row 3 by 1 over 13. Let me make a little bit more room so I have space to work. And what we want to do now is make the entries above this leading 1. We want these entries to both be 0. So I'll leave row 3 the same, but I'll replace row 2 with row 2 minus 15 times row 3. And now I'll change this negative 4 into a 0 just by doing row 1 plus 4 times row 3. Let me zoom back out, and let's now make this 10, which is the leading entry in row 2, let's make it become a 1 by multiplying all of row 2 by 1 over 10. So I'll continue that down here. And the last thing we have to do is get the number above this leading 1 to be a 0. So this negative 2 has to become 0. I could do that by replacing row 1 with row 1 plus 2 times row 2. And now this matrix here actually reveals to us the answer to this system. Remember, this part of the system is the coefficient matrix. Those columns represent the coefficients of the variables x, y, and z. So each of the 3 rows corresponds to an equation of our system. The first row of our matrix tells us that 1x is equal to 3. The second row tells us that 1y is equal to negative 5. And the third row says that 1z is equal to 1. So our system of linear equations has one unique solution, but that's not always the case. Let me give you a couple examples for what the reduced row echelon form could look like that would indicate to you that this is not the scenario. So let's erase what we have above. So this scenario is when there is one unique solution. And the system is often called an independent system if there's one solution. But let me also show you what it would look like if there were no solutions or infinite solutions. Let me start by drawing a matrix that's in reduced row echelon form that has no solutions. I know this matrix would indicate that the system has no solutions by looking at row 3. Based on row 3, I see that 0 would have to be equal to 1. And I know that 0 cannot equal 1, therefore there are no solutions to that system. But what about infinite solutions? Let me draw a matrix that represents that scenario. Based on the coefficient part of this matrix, I can tell there are 3 columns, so there must have been 3 variables in the equations. I'll call them x1, x2, x3. But when I look at the number of leading 1s in my matrix, I see there are only 2 leading 1s, but there are 3 variables. When you have more variables than leading 1s, we know there's going to be infinite solutions. And if I were to try and write the solutions, from row 1, I can see that 1x1 plus 2x3 is equal to 3. And if I were to rearrange that to isolate x1, I can move this 2x3 to the other side. And from row 2, x2 minus x3 is equal to 4. And I could rearrange that to isolate x2. And in the column for x3, there are no leading entries. 2's not a leading entry, negative 1's not a leading entry, and 0's not a leading entry. Which means that x3 is what we call a free variable. So you could pick anything you wanted for x3, and then based on what you pick for x3, that's going to alter your answers for x1 and x2, which is going to create an infinite number of answers that'll satisfy your original system of linear equations. Must know number 5, matrix multiplication. Let's say I have 2 matrices being multiplied together. How I find the product of these matrices is by finding the dot product of each row from the first matrix and each column of the second matrix. And if you don't know what dot product is, it's just the sum of the products of corresponding entries. And in order to be able to do that dot product, the shapes of these matrices has to meet a set of criteria. Notice in this example, the first matrix is a 2 by 2 matrix. It has 2 rows and 2 columns. And the second matrix has 2 rows and 3 columns. So it's a 2 by 3 matrix. In order for multiplication to work, these two numbers have to match, meaning the number of columns from the first matrix has to match the number of rows from the second matrix. And then these numbers indicate what the size of the resulting matrix is going to be. So the product of these matrices is going to result in a 2 by 3 matrix, which means there are going to be 1, 2, 3, 4, 5, 6 entries in this matrix. To find the entry that goes in row 1, column 1, I find the dot product of row 1 from my first matrix and column 1 of my second matrix. And to find that dot product, I find the sum of the products of their corresponding entries. So the first entry in the row times the first entry in the column, 2 times 4, plus the second entry in the row times the second entry in the column, 3 times 1. And then I'll just repeat this process 5 more times. To get the entry in row 1, column 2, I'll use row 1 of my first matrix and column 2 of my second matrix, and then find the sum of the products of their corresponding entries. 2 times 3 plus 3 times negative 2. And then row 1, column 3, use row 1 of the first matrix, column 3 of the second matrix, and then find the dot product of their corresponding entries. 2 times 6 plus 3 times 3. And then to find the 3 entries that are in row 2 of my product matrix, I'll be finding the dot product of row 2 of matrix 1 with all 3 columns of matrix 2. So row 2 and column 1, row 2, column 2, and row 2, column 3. And now I can just simplify all 6 of those entries. And I get the matrix 11, 0, 21, negative 1, 13, negative 9. So that's how you multiply matrices. Must know number 6, the determinant of a 2 by 2 matrix. Now we're starting with the determinant of a 2 by 2 matrix because the determinant of a 1 by 1 matrix is just itself. And we'll actually need to know that property as we do this example here. Let's start by defining a determinant. For any square matrix, so for any n by n matrix, we'll call it matrix A, the determinant of matrix A, which has a couple different notations, can be calculated by expanding along any row or column. If we're expanding along row I, the formula for calculating the determinant of A would equal the sum from j equals 1 to n of the product of each element in row I, so aij, with its corresponding cofactor. So in row I, we do each element times its cofactor and add it all together. But what is a cofactor? To find the cofactor of any element in the matrix, you do negative 1 to the exponent of the row number plus the column number times the minor of element ij. But what's the minor of element ij? Well, any minor element is just the determinant of the submatrix obtained by removing the ith row and jth column. But remember, since we have a 2 by 2 matrix, when we remove a row and a column, what we're left with is just a 1 by 1 matrix. And the determinant of a 1 by 1 matrix is just the value itself. So calculating the minor of any element in a 2 by 2 matrix is really simple. And you'll see how that works as we do an example. Let's say we have matrix A. Now, because this is a square matrix, it's a 2 by 2 matrix, I know I can calculate a determinant. And to calculate the determinant, I have to pick any row or column in this matrix to expand across. It wouldn't matter which one, we'd get the same answer in the end. So I will just pick row 1. And what this formula tells me to do is to take each of the values in row 1, multiply them by their corresponding cofactor, and then add those products together. So I would have to do the element in row 1, column 1. So A11, multiply it by its corresponding cofactor, plus do the element in row 1, column 2, and multiply that by its corresponding cofactor. Well, I know the value of elements A11 and A12. It's 3 and 5, but I'll have to calculate their cofactors. So let me start by calculating the cofactor of the element in row 1, column 1. Using the cofactor formula, I would have to do -1 to the power of 1 plus 1, and that gets multiplied by the minor of the corresponding element. So that would be times the minor of element 1, 1. Well, -1 to the power of 2 is just 1, and the minor of the element in row 1, column 1, well, to calculate a minor, I remove row I and column j. So that would mean remove row 1 and column 1, and then find the determinant of the remaining submatrix. The remaining submatrix is just a 1-by-1 matrix, so its determinant is just its own value, 7. Which means the cofactor of the element in row 1, column 1 is 1 times 7, which is 7. And now let me make a bit of room so we can calculate cofactor 1, 2. To find the cofactor of the element in row 1, column 2, so the cofactor of 5, I would do -1 to the exponent of 1 plus 2 times the minor of the corresponding element. Well, -1 to the power of 3 is -1, and then to get the minor of the element in row 1, column 2, I would have to eliminate row 1 and column 2 and find the determinant of the remaining submatrix. The determinant of 2 is just 2. So -1 times 2 is -2, and I can now sub in for all 4 of the values required to calculate the determinant of matrix A. 21 plus -10 is 11. So the determinant of this matrix is 11. But if we have specifically a 2-by-2 matrix like this one, there's a shortcut. Let me show you that shortcut and how it would work. So I'll redraw matrix A that we started with, and then to find the determinant of matrix A, because it's a 2-by-2 matrix, I can just find the product of the numbers in that diagonal, 3 and 7, and then subtract the product of the numbers in that diagonal, 2 times 5. And notice that would give me the same answer, 21 minus 10, which is 11. Must know number 7, the determinant of a 3-by-3 matrix. Let's say we have matrix B. If I want to calculate its determinant, it will probably be helpful if I remind you of the formula for calculating the determinant of any n-by-n matrix. So let's say we're finding the determinant of matrix B. And let's say we're expanding across row I of matrix B. I would find the sum from j equals 1 to n of each element in row I times its corresponding cofactor. So for this matrix, we can pick any row or column to expand across. To keep it consistent, I'll expand across row 1. So to find the determinant of matrix B, I would need to do the sums of the products of each element in row 1 times its corresponding cofactor. Now, I know the value of all of the elements in row 1, it's 1, 5, and 0, but I'll have to calculate these 3 cofactors. I'll start by calculating the cofactor of the element in row 1, column 1 up here. I know to calculate a cofactor, I do -1 to the power of the sum of the row and column indices, so to the power of 1 plus 1, times the minor of the element that's in row 1, column 1. -1 to the power of 2 is just 1, and then to calculate the minor of the element that's in row 1, column 1, I have to imagine removing row 1 and column 1 from my matrix, and then find the determinant of the remaining submatrix. So I need the determinant of the matrix 4, -1, -2, 0. And in the last section, I showed you the shortcut for finding the determinant of a 2-by-2 matrix. I just do the product of that diagonal, 4 times 0, minus the product of this diagonal, -2 and -1. And if I simplify that, I get -2. Now I'll make a little bit of room so I can calculate my remaining 2 cofactors. If I continue expanding across row 1, the next cofactor I have to find is for this element, the element that's in row 1, column 2. Cofactor 1, 2 would be equal to -1 to the power of 1 plus 2 times the minor of the element that's in row 1, column 2. -1 to the power of 3 is -1, and the minor of element 1, 2, if I eliminate row 1 and column 2, I then just find the determinant of the remaining submatrix. So I'd have -1 multiplied by 2 times 0 minus 0 times -1, which gives me -1 times 0, which is 0. And then continuing along row 1, the last element I have to find the cofactor of is the element in row 1, column 3. So I'll give you that solution quickly here. And now that I have all 3 elements of row 1 and all 3 of their cofactors, I can sub into my determinant formula. And evaluating this expression gives me a determinant of -2. And now let me show you a shortcut you can use for any 3x3 matrix if you want its determinant. The shortcut, we'll need a copy of the original matrix B, and then what we do is we copy the first 2 columns to the right of the matrix. And then what I do to find the determinant of B, I find the sum of the products of the numbers in these 3 downward diagonals. In the first diagonal, the product of 1, 4, and 0 is 0, plus the product of 5, -1, and 0 is also 0, plus the product of 0, 2, and -2 is also 0. And then I subtract the products of the 3 upward diagonals. For the first upward diagonal, the product of the 3 numbers 0, 4, and 0 is 0, minus the product of the 3 numbers that make up the next upward diagonal. -2, -1, and 1 have a product of 2, minus the product of the 3 numbers in that diagonal is 0. And then we can just evaluate this expression, which is just -2. Must know number 8, how to calculate the inverse of a matrix. Now that you know how to calculate the determinant of a matrix, we can look at one of the main applications of determinants, which is to help find the inverse of a matrix. An n by n matrix, we'll call it matrix A, is invertible, meaning it has an inverse, if there exists a matrix, the inverse matrix of A, so that the inverse matrix of A times matrix A equals the identity matrix. And the formula for calculating the inverse of a matrix is as follows. To find the inverse of matrix A, you do 1 divided by the determinant of matrix A, and multiply that by what's called the adjugate, or sometimes the adjoint, of matrix A. And within this formula, there's a couple things to note. We know we can only calculate determinants for square matrices, so that means the only matrices that are invertible are square matrices. Also, the adjugate of matrix A is just equal to the transpose of the cofactor matrix of matrix A. And one other thing we should note is that if the determinant of the matrix was 0, we would have 1 over 0, which is undefined, which would mean that the matrix is not invertible. And we call that a singular matrix. And a determinant being 0, telling us that matrix A is not invertible, also actually tells us there's not a unique solution to this system of equations. But we'll get more into that in the next section. So let's go ahead and do an example where we use this formula to calculate the inverse of a matrix. Given this matrix A, let's find the inverse of matrix A. In this formula for the inverse, I need 2 things, the determinant of matrix A and the adjugate of matrix A. Let's start by finding the determinant. Since this is a 3x3 matrix, I know there's a shortcut for finding the determinant. I just rewrite the first 2 columns beside the matrix, and then find the sum of the product of these 3 diagonals. So this first diagonal is 4 times 5 times 3, which is 60, plus 2 times 2 times 2, which is 8, plus 1 times 3 times 1, which is 3. And then I subtract the products of these 3 diagonals. So I have to subtract 2 times 5 times 1, which is 10, 1 times 2 times 4 is 8, and 3 times 3 times 2 is 18. And if I simplify that expression, I get a determinant of 35. And now I need to find the adjugate of matrix A, which I know is equal to the transpose of the cofactor matrix of matrix A. So we'll start by finding the cofactor matrix of matrix A. I'm going to have to find the cofactor of all 9 elements of matrix A. Let's start with the element that's in row 1, column 1. To calculate its cofactor, I do -1 to the power of 1 plus 1. The exponent is always equal to the sum of the row and column indices of the element. And then that has to be multiplied by the minor of this element. And remember, the minor of an element is just the determinant of the submatrix we get when we eliminate the row and column that the element is in. So I now just have to find the determinant of that submatrix. So doing this calculation will give me the cofactor of 4, and to get the whole cofactor matrix, I have to do that calculation for all of the terms in the matrix. And now that I have all 9 terms of this matrix, I need to simplify each of them. So let's start with the element that's in row 1, column 1 of our cofactor matrix. -1 to the power of 1 plus 1 is just 1, and then I need the determinant of this 2 by 2 matrix. And I know to find the determinant, let me zoom in a bit, I just have to do the product of that diagonal, 5 times 3 is 15, minus the product of this diagonal, 1 times 2 is 2. 15 minus 2 is 13. So I know the first element in my cofactor matrix is 13. And then I can repeat that process for the other 8 elements in this matrix. And I now have the cofactor matrix of matrix A. But what I need in my inverse formula is the adjugate of matrix A, which is the transpose of this cofactor matrix. So I have to transpose this matrix. The transpose of the cofactor matrix is the matrix that just has the rows and columns switched with each other. So row 1 of the cofactor matrix becomes column 1 of the transposed version of that matrix. And I'll do the same thing with row 2 becomes column 2 and row 3 becomes column 3. And now that I have the transpose of the cofactor matrix and the determinant, I can use this formula. I'll have to make a little bit of room, and then I'll sub into the formula. The inverse of matrix A equals 1 over 35. And since this value is not 0, since the determinant is not 0, I know that the matrix does have an inverse. So that means there is actually a unique solution to this system, which we'll get to in the next section of this video. And that has to be multiplied by the adjugate of matrix A, which is this transposed cofactor matrix. And then what we could do if we wanted to go further is we could multiply all 9 elements of this matrix by the scalar in front. And that would give me the following matrix. And there we have it. There's the inverse of matrix A. Must know number 9. Finding the inverse of a matrix using row reduction. This is an alternate way. Instead of using the inverse of a matrix formula, what we can do is we can make an augmented matrix out of the matrix we want the inverse of. We'll call it matrix A, and we'll augment that with an identity matrix of the same size as A. And then we use elementary row operations to transform that matrix into the matrix I augmented with the inverse of matrix A. And how we do that is we focus on doing row operations to transform matrix A into an identity matrix. And when we do that, the operations that do that transformation are going to make this identity matrix go into the opposite or inverse of matrix A. So let's see how that works. Let's say we have matrix A, which is just a 2 by 2 matrix. Let's find the inverse of that matrix. So we'll construct our augmented matrix by augmenting matrix A with an identity matrix that's also 2 by 2. So that would look like this, 1, 0, 0, 1. And then we'll use elementary row operations to try and make this matrix into this identity matrix. I'll start by making 4 my first pivot value and then making the 2 underneath it become a 0. And I'll do that by replacing all of row 2 with 2 times row 2 minus row 1. Now that the upper triangular matrix is done, I'll make the value above this leading entry be a 0. So above the 5 is 7. I want that 7 to be 0. So I will replace all of row 1 with 5 times row 1 minus 7 times row 2. And now I need my leading entries to be 1, so I need the numbers in this diagonal to be 1. I can do that by multiplying row 1 by 1 over 20, and by multiplying row 2 by 1 over 5. And now the process is done. The original matrix A has been transformed using row operations into the identity matrix, which means the identity matrix has been transformed into the inverse of matrix A. So I can conclude now that the inverse of matrix A is this matrix right here. And now that you know a couple ways for finding the inverse of a matrix, we should also talk about how we could use the inverse of a matrix to help find the solution to a system of equations. So let me make some room to talk about that. Inverse matrices can be used to solve linear systems if we first write them in matrix form, which means we write the system of equations in the format A times X equals B, where A is the coefficient matrix, X is our variable vector, and B is the constant vector. And the reason we would want to write the system of equations in this matrix form is because if I multiplied both sides of this equation by the inverse of matrix A, On the left side, the inverse of matrix A times matrix A, I know is just the identity matrix that's the same size as matrix A. And multiplying by an identity matrix is like multiplying by 1 when dealing with matrices. So the identity matrix times the column vector x is just equal to x. So this tells us to get what the column vector of variables is equal to, we just do the inverse of matrix A times the column vector of the constant values. So let's see how that would work. Let's say we have a system of two linear equations. I could write this system in matrix form by doing the coefficient matrix, which would be the matrix 4, 7, 2, 6, times the column vector of the variables, and our variables are x and y in both of the equations. And that would be equal to the column vector of the constants, 6 and 3. And what I tried to show you down here is that if we multiply both sides of this equation by the inverse of the coefficient matrix, we end up getting the column vector of variables isolated. And this matrix, we actually already found the inverse of it earlier, and I wrote it down up here. It's this matrix right here. So I'll multiply both sides of my equation by that matrix. On the left side of the equation, I have matrix A times its own inverse. I know that's going to be the identity matrix. And on the right side of the equation, I have two matrices that I have to multiply together. I have a 2 by 2 matrix being multiplied by a 2 by 1 matrix. Because these elements match, I'm allowed to multiply those matrices together, and the product is going to be a 2 by 1 matrix. To get the element that goes in row 1, column 1, I do row 1 of the first matrix dot product with column 1 of the second matrix, which means do 3 over 5 times 6 plus negative 7 over 10 times 3. And to get the element in row 2, column 1, do row 2 dot product with column 1. Negative 1 over 5 times 6 plus 2 over 5 times 3. And now I just have to simplify. On the left, when multiplying by an identity matrix, you just get itself. So the column vector of variables, x, y, would be equal to, these two rows simplified, go to 1.5 and 0. Notice for this system, we got a unique solution. When x is 1.5 and when y is 0, both of these equations are satisfied. And finding that one unique solution will happen if your coefficient matrix is invertible, because if it's invertible, you're able to use this process to narrow it down to the one unique solution. If it's not invertible, meaning its determinant would have been 0, then you would know you don't have a unique solution, and you'd have to use a different strategy to find out if you have infinite solutions or maybe no solutions. Must know number 10, Cramer's rule. Cramer's rule is a method for solving a system of linear equations where the matrix must be square and it has to have a non-zero determinant. For it to have a non-zero determinant, that means there is a unique solution to the system of equations. So Cramer's rule only works to find us the unique solution of a system. And how Cramer's rule works, for the matrix equation of a system, ax equals b, we can get the answer for the variable xi by doing the determinant of AI divided by the determinant of matrix A. But what is matrix AI? That's the important thing you have to know here, and it's actually quite easy once we do an example. Matrix AI is matrix A with the ith column replaced with vector B. And although this may sound a little bit confusing right now, when we do an example, you'll see how easy it is. So let's say we have a system of two equations with two variables each. I could solve this system of equations by first writing the system in matrix form. And then before I go ahead and use this formula to find the value of the variables, I notice in that formula, I need the determinant of A. So this formula is only going to work if my determinant of A is non-zero. So let's start by finding that determinant. The determinant of matrix A, well, remember matrix A is just this 2 by 2 coefficient matrix right here. I can find the determinant of a 2 by 2 matrix by subtracting the product of the diagonals. That would be 3 times 4, which is 12. And then I subtract this product of negative 5 times negative 2, which is 10. And 12 minus 10 gives me 2. So since my determinant is non-zero, I know that my system has a unique solution, which means I can use Cramer's rule to find those solutions, which means this formula right here. And when I use this formula to solve for x1, I'll be replacing these i's with 1, which means I need the determinant of matrix A1. But what is matrix A1? Let's write that down as well. Matrix A1 is just matrix A, but the first column of it is going to be replaced with the column vector of my constants, 6 and 8. So instead of the first column being 3, -5, it gets replaced with 6, 8. But the second column stays exactly the same. And when I solve for x2, I'm going to need matrix A2. Matrix A2 is just matrix A, but its second column is replaced with the constant vector. Its first column stays the same, but its second column changes to 6, 8. And now let me go ahead and use this formula. When calculating the value of x1, I do the determinant of A1 divided by the determinant of A. Well, we have the determinant of A. We already calculated that to be 2. But now I need the determinant of matrix A1, which would be 24 minus -16. That's 40. Which means x1 is 40 divided by 2, which is 20. And x2 would be the determinant of A2 divided by the determinant of A. Determinant of A is 2. And we need the determinant of the A2 matrix, which would be 24 minus -30, which is 54. And 54 divided by 2 is 27. So based on Cramer's rule, I see there is one unique solution to this system. It's when x1 is 20 and when x2 is 27. Jensen Math!